AI is probably the biggest buzzword we have in tech right now. Every single product's trying to turn AI into a feature. We have a bunch of products being built around AI, and we heard a lot about it. And though it's like this big buzzword that we all know what it's talking about, we don't really know what it actually means. The movies have prepared us for the apocalyptic AI scenario, where it may show up naked in a bar and starting a fight. So the movies have not prepared us, though, for this stage of AI, because we're not even close to singularity or whatever else. AI right now is here to help, but it's not the same thing. It's not like you're going to plug AI in your product and it's going to become a sentient being and take over the world.
I'm sorry, Dave.
So if you did any kind of research on AI from the tech side and you talk to people, you probably heard the term or read the term vector database everywhere. And what the heck is it? Vector is a kind of array. And the vector database is a specialized database to store data and manage as high-dimensional vectors. It enables efficient similarity and semantic matching. So what vector databases do is use machine learning embeddings to represent complex data like text, images, or audio as numerical vectors. So it's basically going to break down that piece of content into these high-dimensional vectors. And it's not going to work with exact matches as opposed to the other more traditional databases that we know of. It's going to use similarity. So here's a little metaphor for you. Remember that scene in Iron Man where, Iron Man 2 actually, where Tony Stark just expands a huge graph of interconnecting dots? That's actually a decent rough representation of what AI is. So it's a multi-dimensional environment, so much bigger than our three-dimensional world, where each point in that vector is a coordinate. And by putting together a coordinate that's built from thousands of points, we are enabled to then define the proximity or the similarity in this case of between each of those points. And that's how we build a model. So that's why vector databases are great for this semantic similarity search by performing searches that find the nearest neighbors of each data point and essentially supporting AI and machine learning to perform context-aware, rapid, and efficient data retrieval. And talking about similarity search, there are actually 3 systems in which it operates. We can use cosine similarity, dot product, or Euclidean distance. And each of them perform better for a certain kind of data. So understanding the shape of your data and how each of these points are going to relate to each other is essential in order for you to choose the right system with which to perform your similarity search. In a very hand-wavy way, let's check a rule of thumb for each one of those. So cosine similarity is used to measure the angle between each of those points. So in this case, if the magnitude, the sheer number of your coordinate is less important, you can choose cosine similarity, which makes it great for text and semantic similarity. Dot product captures the linear correlation and alignment. So it's great for establishing relationships between multiple points in features. And the Euclidean distance calculates a straight line distance. It's good for dense numerical spaces since it highlights the spatial distance between them. Now that we understand what vector databases are and how similarity search operates, we can finally reach the biggest buzzwords of them all: large language models and their sibling, the small language models. A language model is an AI system trained to understand, predict, and generate human-like text. By learning the statistical patterns and relationships between the words and phrases in a large text dataset. In other words, it's going to perform the similarity search to understand the relationship between each entry of your vector database, and then it can understand, predict, and generate human-like responses to your prompts and queries. So in a system like these models, language is represented as a probabilistic sequence. So it's immediately capable of completion, translation, and conversation because it can estimate the likelihood of word combinations, and it learns from reaffirming the patterns and adjusting based on new entered data. That's what we call when it learns. By reaffirming the answers to your prompt, some of those entries in your vector database are going to grow in the similarity score between each other, and that's going to refine your language model. And so these language models can then be either large or small in categorization. The large language model is built with a large data set. And by large, I mean billions of parameters, like up to 70 billion. This enables them to create human-like responses in diverse knowledge domains. So think of them as big generalists, which makes them not only versatile, but extremely powerful. But as a consequence, training them demands a lot of computational work. With a smaller data set, like a small language model that goes from 100 million to 3 billion parameters, they take significant less computational effort, which makes them less versatile and much better suited for specific tasks with more defined constraints, especially because they can be deployed more efficiently and they have faster inference when processing input. In other words, a large language model knows something about everything. Think about when you left high school, where you knew a little bit of biology, you knew a little bit of geography, you knew a little bit of literature and whatever else, but you didn't know very specific questions. So if I'd ask you something that's very domain specific, like what is hoisting in JavaScript, you might not know that because that was not content in your school, at least wasn't in mine. But as you go for a smaller language model, I don't remember anymore a lot of things I learned in botanic in school, for example, but I do know very well what's hoisting JavaScript. And so I'm now grew from a big generalist to more of a specialist in terms of I am a developer. So that's more or less, in a very hand-wavy metaphor, the difference between a large language model in this case and a small language model. But you can also have other strategies to improve the processing of your large language model and keep that much larger processing power and much larger data set while making it specific and talented for your targeted use case. And there are different strategies for that. The first one we're going to talk about is fine-tuning. Fine-tuning an LLM involves training on a specific dataset to adapt a pre-trained large language model to perform better in a particular domain or task. So this process adjusts the model's weight through additional target training. It enables the model to develop more nuanced understanding and generate more accurate, context-specific outputs without completely retraining the entire model from scratch. So you save all that initial large computation that you've done, and you refine it for a specific task. The way fine-tuning works is through multiple iterations when learning rate, weights, and batch size are adjusted while providing a high-quality dataset. Every iteration evaluates the performance of the model to this specific task you want it to improve on. So this is a good approach when you want a model to be good in a very particular task. For example, creating summaries of nutritional scientific articles, correlating symptoms with a subset of possible conditions. Like, for example, I live in Germany and I want to train an LLM to, if I put the symptoms, it's going to give me possible disease that happened in Germany. It's not going to give me like a tropical disease or something like that, even if the symptoms kind of correlate. So I can fine-tune it to my more target context in this particular situation.
It's never lupus.
Or if I'm creating an LLM to summarize talks in a tech conference, I can provide it with extra context so it's not going to butcher buzzwords or it's not going to butcher technical terms in this case. Besides fine-tuning, another technique is called RAG, Retrieve-Augmented Generation. If you want a definition that fits in a tweet, a RAG enhances the LLM's context, providing it with a more comprehensive understanding of the topic. So the way it works is by retrieval and pre-processing and through ground generation. What does that mean? RAGs leverage powerful search algorithms to query external data. So you can use some kind of algorithm to query external data. It can be a web page that you're scraping. It can be a knowledge base that you're querying. It can be other databases, for example. And once retrieved, the relevant information goes through a pre-processing. It includes some tokenization, stemming, and removing of stop words. So it's basically optimizing it to be turned into a vector. Once pre-processed, it's then incorporated into the pre-trained LLM. And this is going to enhance the context by providing it with more comprehensive understanding of that particular topic. And it not only allows the LLM then to provide you with more precise and informative responses, but also ends up being much more engaging. So in summary, it's going to retrieve some other kind of data set, scraping, database, whatever, and it's going to add context to the LLM. Think of it when you arrive late at a meeting and somebody gives you a big summary of what has been discussed. That's the RAG. So a RAG is extremely good for data-driven responses since it provides access to fresh information. It's much, much, much cheaper to bring extra data to your RAG than to do fine-tuning or even to retrain your LLM, obviously. So with a RAG, you can have more current information as time goes by. And as a consequence of that, it's more accurate with facts because, the world keeps changing. And with RAG, you are bringing current information constantly to your agent. So that makes a RAG particularly useful for chatbots, assistants, and basically any other kind of agent where the output depends on quality access to domain-specific knowledge. So we talked about how RAG grabs the information in the wild and prepare it to be added to the LLM. The actual action of adding it to the LLM is what we called embedding. Embedding is a statical vector representation of data. Remember, vector database, and then RAG brings like other kinds of data, and then you need to turn that into a vector. So embedding is doing that. It's going to grab all that information that can be text, can be numbers, can be whatever you want. And after we remove the stop words and we prepare it, it's going then to turn those into numeric values or those coordinates that we're going to have a huge vector of. And by doing the embedding, we're capturing the semantic meaning of this data. So then we can establish the patterns and the relationships for the similarity search. And different language models are going to have different levels of precision embedding. So for example, you can have embeddings that range from 384 dimensions all the way to 2048. So for example, OpenAI, which is one of the most popular text embeddings that we have, they have text embedding 3 small, which is 1536 dimensions and reasonably accurate to generate decent embeddings for average use cases. But on the other hand, it also has the text embedding 3 large, and that's 2 times more dimensions. That's 3072. So naturally it takes more computational work, which makes it more expensive and more precise for your RAG. I hope that gives you like a nice overview about what AI actually means when we say that, and that for now your job's safe because there's still a lot of work to be done in terms of applying these technologies and experimenting with these technologies and training these technologies and making sure they don't hallucinate on you and provide accurate responses. And soon enough, we're going to check about how to create our first RAG. So make sure to subscribe and not lose that one because then we get into actual coding with AI. So Let me know in the comments below how that helped you and what kind of stuff you're building with it and what you would like to see. And otherwise, I'll catch you up on the next one. Bye.